All right, ladies and gentlemen, this is the video for Unit 5 Aqueous Chemistry in Chapter 4. We are going to cover some of the notes that we would have covered today. I'm unable to attend class, so I am expecting that you take these notes and that when we come back the next day that you are prepared on Thursday. This is where we left off yesterday, talking about the activity series, or at least the last time we took notes. Yesterday in lab, you did some single replacement reactions based on location of the metals. You would have seen that some of them reacted and some of them didn't. And some of you made some small mistakes in not looking at your activity series, and that's why we have to look at our activity series to see which ones are more popular. The more popular the element or compound is, the most likelihood that we're going to see it in a compound. The less popular elements we see in their natural stable states, we see them and can actually find them in nature as the metal themselves. We don't find them in a compound. They're not popular enough to potentially have a friend all the time. Lithium, potassium, barium, calcium, sometimes we can. Sodium definitely is kind of one of those ones that we don't find them in nature with a friend. We always find them with a friend. We don't find them without a friend. They're always that person that always has to have somebody with them all the time. And we all know some people like that. So here are some examples and we have to determine whether or not these reactions will happen. And if they do happen, we'll predict their outcome and then balance them. So the first one, is sodium going to replace potassium? And so we look at and see that potassium is right here and sodium is down here. The sodium is by itself and is less popular, lower on the activity series than potassium is. Since potassium is more popular, has a friend, chlorine is not going to leave potassium. It's going to stay there, so no reaction is going to happen. The next one that we look at, let's see, is whether or not magnesium is going to replace zinc in the zinc to nitrate. So we pay attention and look at, okay, where is magnesium? Here's magnesium. And then we look at where zinc is. All right, well, which one is more popular? Magnesium is more popular and therefore will most likely have a friend. And since zinc is less popular, nitrate will leave zinc, so to speak, and be replaced by it. Now, when you write these in on the other side, I still, again, like to write them out in the same order in which we find them. One of the nice things about this first example is the charges of both zinc and magnesium are the same. So when we write them out, we would see that the charges don't change. That's a solid as well. And that is our aqueous solution. That's an A there. And put that in parentheses. So it's AQ and zinc. And so we see that, and it balances out because the charges balanced out. And that's how that works. It's real nice, and it works out real well for us. And so the worry is just trying to figure out whether or not this will be replaced. The next example we need to look at, and we see that lithium, the most popular element, it's the cat's meow, is the most popular element on the activity series, and it is definitely, it will replace any metal. Now it's gold is the one that's in the least popular. It will lose its friend. I'm sorry, that's just how life happens sometimes. And so when this happens, we see that lithium. Now we have to pay attention to charges. If we look at our periodic table, we'll see that lithium has a positive 1 charge, and sulfate has a negative 2 charge, and those don't match up. So we see that it is LiSO4. I'm not sure why I have the parentheses here. Those technically should not be there. Those parentheses should not be there. Bad, Peterson. And so lithium sulfate ends up becoming our aqueous solution. And gold, and yes, everyone always thinks about the awesome powers, gold, when they think about gold. And so his AU ends up being the solid gold on the outside. But now we need to balance it. So what do? Well, I have 2 lithiums on my product side and only 1 on my reactant side. So I need to put a 2 in front of the lithium. But that's not the end of the story, because gold has 2 on the reactant side, and therefore we need 2 on the product side. And now for our last one, we are going to look at lead and cobalt. And so we again identify whether which one is more popular. And so we find lead on our chart here, and see that lead is right there. And then cobalt is more popular than lead, and it has a friend. And so guess what will happen? No reaction. Okay. You'll find a number of other examples on your Mastering Chemistry that will definitely help you out when it comes to doing and predicting some of these examples. Now, we're going to kind of switch gears here a little bit and start talking about the different types of solids that we've examined and concentration. It doesn't mean paying attention more, although it probably should help if you do pay attention when talking about concentration. The referencing of that should be Unit 5 that we have earlier talked about. So ionic solids are solids with a cation and an anion, metal, non-metal, or any compound containing a polyatomic ion. Pay attention to those solubility rules. Again, those are things that we definitely come back to constantly. And your solubility rules, again, are Group 1, Rule 1, and your ammonia salts. Then your Rule 2 is your nitrates and acetates. Rule 3 has 3 exceptions. Rule 3 definitely plays with the halides, with the exception of silver, mercury, and lead. Rule 4, SO4, deals with sulfate. There are 3 exceptions on that as well. That would be strontium, barium, and lead. Mercury could be added into that, but we don't deal much with mercury, so we don't have it in ours. And then the last rule is your kind of catch-all, is your all other salts are insoluble, meaning they form a solid, and therefore, except for your group 2, heavy group 2s, so that'd be calcium, strontium, and barium sulfide, and hydroxide. Those ones are soluble, or at least slightly soluble. So we look at these, and the idea of polarity is something else that we bring in and is definitely going to be important. And the idea of polarity, we talked about that in Unit 3.5. For some of you, that might seem like a lifetime ago, but Unit 3.5 dealt with polarity, the unequalness of the sharing of the electrons, and the polarity comes into those polar molecules or polar molecules based on our covalent compounds. So our nonmetals on those. So we do work with that. Now the big rule that we deal with in polarity is like dissolves like. Even though our ionic solids are not polar, they will dissolve in a polar liquid. Non-polar solids will only dissolve in non-polar liquids. That's why when you get your hands full of engine grease, that you need to use like a Dawn dish soap or Gojo. Those are things that you have to do because otherwise you're just not going to get it off. Or you have to use really hot water. Just regular hand soap does not work very well. It's why it says like dissolves like. The other things is like the why Dawn dish soap cuts the grease. It's kind of because Dawn dish soap has a polar end and a non-polar end when it comes to dealing with the cutting of the grease. And so we're able to get some of that out and understand that based on this idea of polarity, and that we're going to use this idea of polarity as we continue on. Some ways in which we can help things dissolve: stirring, agitating, shaking sometimes, although we won't shake things in the classroom. Usually they also suggest not shaking babies. That's kind of a big no-no. But stirring, we can stir glass stirring rods. A number of you have broken those. But stirring is something that helps the process. I know in the back stockroom, I use a magnetic stirrer that is a magnet that just spins very at high repetition, usually at over 1,000 repetitions per second, or per minute, I think it is, RPM. And it just stirs it instead of me sitting there stirring it over and over and over again. I just send it in there. Some other things that can help things dissolve are temperature. A couple of you, I think at least one of you is doing your paper on gases and being dissolved in hotter liquids or something like that. And so you're going to see how temperature affects whether or not something is being dissolved in. And so we have to pay attention to the temperature. That's why a lot of chemical compounds will say whether or not the temperature's there, at what temperature does this happen, was it a constant, and some of those types of things, and that's why temperature is such a big deal. That's why in your, say, a hot water heater, the solutions will come out, or the solids will come out of solution at higher temperatures. Even at a hot water temperature, they come out of solution. Well, that means sometimes that things can go into solution at higher temperatures. Most people will put salt in their water when they're boiling noodles for like spaghetti or something like that. They feel it increases the temperature, or actually just all it does is elevate the boiling point, and it actually doesn't increase the temperature. The salt will dissolve, and it dissolves a lot. If you've ever made sugar candy, you increase the temperature, you can get more and more and more and more and more sugar to dissolve at higher temperatures, so that's where you kind of look at it. Some of the other ways in which you can get this to work as well is decreasing surface area of the dissolving particles. So crushing your grains for a couple labs that we're going to do later on, it's going to be important that we use our mortar and pestle to crush the grains, make them smaller, easier even, and then usually you add some of these other things together. So you can stir, decrease surface area, and stir. A lot of times you have to be very careful about whether or not you increase the temperature because too much of an increase in temperature can have an effect on whether or not the chemistry is going to actually pan out or play out. And so you have to be very careful about increasing your temperature in some cases. But a lot of times, stirring and surface area are the big ones. Stirring happens the most. That's how you get your Kool-Aid as well to dissolve in your water that you use. Stirring it, that's why they tell you to stir. Otherwise, it's just all going to be at the bottom and it's going to stay there until time goes across. So pay attention to some of those types of things as we kind of continue on and are going through the lab. Liquids, dissolving in liquids is kind of a tricky thing. It really comes down to are they mixable or inmixable or not mixed together? And so we can kind of pay attention to how the terms look. Miscible means mixable, is how I usually like to look at it. So miscible is mixable. Okay, so you can mix the two liquids. Ethanol and water, we've mixed it. They will mix. They will actually and sometimes decrease. Water and vinegar, mixable. Okay, vinegar is a polar molecule. Water, also a polar molecule. That's why they mix. But some things are immiscible, meaning they are not going to mix. So immiscible means they are not going to mix or not soluble in each other. Oil and water, oil and vinegar. We've done the hexane in water in the lab. And so things that are not mixable are immiscible. And this rule or idea of like dissolves like still applies. We use it for solids to liquids, but we also use it for liquids to liquids. Are they miscible? Are they able to mix? And so you have to really kind of pay attention to some of those things as we continue on and move forward. Can these two mix? Usually yes or no. And you have to remember this idea of polarity, and that's why it was stressed then. Try not to forget it, even though a lot of you probably have forgotten it. So this idea of miscible, mix, immiscible, well, they don't mix. It's not. It's kind of the prefix for not. So paying attention to those terms is definitely something important as we move forward. So it does have its exceptions, as we have found time and time again in chemistry. Every rule kind of has some exceptions, and it's actually sometimes easier to talk about the exceptions to the rule than actually talking about saying, well, making up, well, not everything applies to that, but this applies. It's easier to say, hey, you know what, like dissolves like. And 90% of the time, you're going to be right. One example we have is this water is a polar, but you have a trichloromethane is only slightly polar. They're immiscible. They will not mix. Water and dimethyl ether or diethyl ether, they're both polar, but they're immiscible. That was why when we did one of our non-laboratory based activities, you used a dimethyl ether. And that would have, the dimethyl ether had the kind of looked like this, where you had the oxygen and you had a methyl group on each side. Dimethyl ether is the same thing. Both technically it's polar, but you have these issues of that they're immiscible. It's technically polar, but because it's immiscible, a lot of people will think initially that it's non-polar because of this immiscible solutions. They don't mix. And so we have to be very, very careful about that. And that gets into some chemistry that we're not going to get into, we're not going to talk about, but just every now and then when you see like, hey, why is this not mixing? It should, but it's not. And it's so this idea is like, oh, okay, I remember Peterson telling me that not everything mixes. And there are ways sometimes for us to kind of sneak around that as well. Phenolphthalein is a non-polar solid, and you use ethanol to dissolve that. And ethanol is a polar liquid. And so, but you use it to dissolve phenolphthalein. And then you take water and you mix it because ethanol and water are miscible. And so you kind of have to, the more chemistry you know, the what you can get around some of these little problems that we have sometimes of going, how do I deal with this? And so, that's how we get phenolphthalein solutions, and we'll definitely see enough phenolphthalein in the next coming weeks when we do some of our concentration labs, that you're going to see it. And how do I get that into solution? By kind of using chemistry and some of these exceptions to the rules to get it to actually go into solution, as we can kind of see. That there are sometimes there's exceptions to the rules, and that's how it works. Three terms that we don't use a lot in chemistry, but we do use them, and that is the idea of a saturated solution, an unsaturated solution, and a supersaturated solution. A saturated solution is a solution that has the most solute dissolved at a given temperature. We have to be careful about that given temperature. As we can see from a previous slide, that you increase the temperature, you can increase the amount of stuff that is dissolved in. And therefore, you have to be very, very careful about that. A unsaturated solution can be less. And this is really tricky, that 1 gram less salt in water at 20 degrees technically is unsaturated if it's 1 gram less than a saturated amount. And that's why we really try not to use it. And that's why we'll use some terms that we'll talk about on Thursday that mean a little bit more to us in chemistry than these do. A supersaturated solution is something where you have more solute, more solid that dissolve than you should. That's just how it is sometimes, and it's really tricky to get these. Making that rock candy from out of sugar is something that you do. You take the string and you roll it in a little bit of sugar ahead of time, and you kind of you put it in the solution, and while you roll it in that string in sugar beforehand, is it gives it something to grow onto. It gives it a starting crystal of sorts. And so as supersaturated solutions, they're really finicky. They don't tend to hang out or stay around very long, and therefore we have usually a lot of issues keeping them around, keeping them, what do we do with them? And so we'll worry about a lot of these terms as we move forward. Saturated, again, it's something that we'll use a little bit more. It's one of the easiest solutions to make because it's get as much of it to dissolve. Usually it's saturated if you still have chunks of stuff sitting in the bottom after agitating it, after stirring it for so long. Unsaturated is really tricky because it can be almost anything. And that's why these terms are not used very widely. They are important terms that we use, but we're going to use some ones a little bit later that will mean more to us, especially on Thursday as we move forward with this. So that's all we have for notes for today. If you run out of time, please move on and do some of your mastering chemistry, as that would probably be a really good idea to kind of get that started since it's going to be due soon.